In this video, we're going to talk about instantaneous velocity and acceleration. So in the last video, we talked about average velocity and said, hey, it's not a very good measure of motion or very good at describing motion, but we can use it to get a better description, and that's about what we're going to do now. So the first thing that we need to talk about is the connection between the average velocity and the slope. So let's just take a look at this example here. If f of t equals 7 minus 1/2 times t minus 4 quantity squared, and I've got an extra parenthesis in there, so that shouldn't be in there. But if that's the position function for an object, find the average velocity from time 2 to time 5. Okay, so that's just what we did in the last video there. We would use the average velocity formula, plug in the 5 and the 2 in the right places. If I plug a 5 in here, I'll wind up with 6.5, right? And if I plug a 2 in here, I'll wind up with a 5. Okay, and then on the bottom, 5 minus 2 is 3. 6.5 minus 5 is 1.5, and divided by 3, that comes out to be a half. Okay, so let's take a look at this on Desmos. All right, so here we are in Desmos, and I have the grid on, but here's the particle right here at time 0. Here I'm using c equals 0, or c for the time instead of the time variable here. So so now we can run it, and that's what the motion looks like from 0 to 10. All right, so that's just what we were doing before, and we were calculating, we just got done calculating the average velocity from time 2, right? So at time 2, the object was at position 5 here, and then at time 5, the object was at 6.5. Notice the scale here is 2 blocks equals 1 unit, so it was at 6.5. Okay, so that's kind of what we were doing before, looking at the motion. So, but to get the connection between average velocity and slope, what we're going to have to do is to take a look at the actual graph of the function, the position function itself. Okay, so now we aren't really looking at the motion of the particle, we're looking at the graph of it. And so what's going to happen here is that this axis is the time axis, okay? And this axis here is the position axis right here. Okay, so for instance, we found that when we calculated, what we just calculated here was the average velocity from time 2 to time 5. So if we look at those points on the graph, right, f of 2 is right here at that point, right? It was 2, and then when we plugged in the 2 into here, we got a 5, right? And then this point over here was when we plugged in a 5 and we got a 6.5, right? So those were the values that we had here. 6.5 was the ending position, right, of the particle, and then 5 was the beginning position, and then it took us 3 seconds, right, to go there. Okay, so that's what those 2 points on the graph of the actual position function would look like, right? And then I can think about the line joining those 2 points right there. Okay, so those 2 points on the position function, and then what I want to do is calculate the slope of that line through those 2 points. So if I do that, and remember each one of these is a half in this scale right here, so this would be 1 unit, right? That would be 2 units, and this would be 3 units here, right? So 3 over, and then 1 unit plus a half more, so 1.5. So the slope of this line would be 1.5, right, over 3. If you look at that, right, that's exactly what we got here, 1.5 over 3. So the slope of that line, right, joining those 2 points is 0.5, right? In this case, it's exactly equal to the average velocity over that time period there. Okay? Let's take a look at another example and see if that's the case in the next example. So same situation, right? Except this time we're going to calculate the average velocity from time 2 to time 4. All right, so we would use that formula, run through the calculations. When we plug in a 4, we're going to get 7. When we plug in a 2, we already know we're going to get 5. This time the time changed from 4 to 2. So the change in time would be 2 seconds or whatever units you're using. So we get 2 over 2 equals 1, okay, for the average velocity from time 2 to time 4. All right, let's look at that. Slide this point over here to 4. There we go, and we can see those values that we got. This point on the position function was 2 and 5 and 4 and 7. So if we want to calculate the slope of the line joining those 2 points, we'll get 1 unit here, 2 units here, so 2 units over, and then 1 unit here and another unit here. So 2 units over and 2 units up. That means the slope of this line is 2 over 2, which is equal to 1. And so notice that is exactly, right, what we got when we did this average velocity calculation. So it turns out, right, and if you look at this formula right here, this is really nothing more than the slope formula from college algebra applied to this function right here. If I have 2 points and I want a graph, or I want the slope of the line joining those 2 points, it's change in y, right, over change in x right here. So that's what it would be. The slope formula is exactly this. So it's no surprise that the average velocity, right, from time 2 to time 4, it's going to be equal exactly, right, to the slope of this line joining those 2 points on the position function there. All right, so there's a definite connection between the average velocity and the slope of the line right here. All right. So what we want to do is find the instantaneous velocity, right? So the velocity, not like from time period 1 to time period 2. We want the velocity at any given moment in time. At 3 seconds in, how fast is it going exactly? Okay. So the approach, right, is to finding that is we're going to take the limit of the average velocity from A to B as B, this E should not be here, as B approaches A. Okay, so what we're going to do is we're going to take the average velocity, say maybe over here, and then we're going to take the average velocity over shorter and shorter time periods starting at 2, right? So maybe not from 2 to 4, but 2 to 3.5. And maybe we would get an even better value, right, here from 2 to 3. Let me turn these points off. And then we're going to make that time period even smaller, even smaller, even smaller here. And I think that the smallest I can make this on Desmos is 2.01. Okay? So you can see that those lines kind of shrink back, and that line right there should look familiar to you. That looks pretty close, right, to the tangent line of this graph at that point. Okay? So if we take the limit of those average velocities, because of that connection between the average velocity and the slope of the line through those 2 points, the limit of the average velocities, right, as you go over smaller and smaller time intervals, it's going to be equal to the slope of the tangent line. And that's exactly what the situation looks like right here. We're taking average velocities. I'm going to take it over a shorter time period, a shorter time period, a shorter time period, a shorter time period, and as short as I can get it. And notice if I can't go back to 2, right, you'll notice that line disappears is because the average velocity formula there, you will be dividing by 0, so it's not even defined there. So the smallest I can make it again is 0, like that. So you can see those lines kind of get closer and closer to the tangent line. What that means is that the limit of those velocities will be equal to the slope of the tangent line. And we know that the derivative, right, gives you the slope of the tangent line. So the big conclusion, right, is that it's the derivative that gives the instantaneous velocity at any time t. Okay, so the derivative actually is like a speedometer, right, for the position function, right? It will tell you, you know, if you're driving along in your car, you can look down at any moment in time and tell exactly how fast you're going. And that's really the purpose that the derivative serves for the position function. Okay, and it's because of this connection with slopes and average velocities that we can do that. So let's take a look at, well, here in symbols, right, we would have the velocity function is equal to the derivative of the position function. So pretty straightforward. Now we know how to take derivatives. So if we want the velocity function, we would just take the derivative. So let's look at an example of that for this same example that we've been looking at. So if f of t is equal to this function here, and that's the position function, find the velocity at time t. Now you may say, well, wait a second, velocity, which one do you mean? Do you mean the average velocity or the instantaneous velocity? Well, instantaneous is kind of a mouthful, right? So we're going to work it this way. And when we say velocity, right, what we mean by default is the instantaneous velocity. And if we specifically want the average velocity, then we will say average velocity. So they are asking you to find the instantaneous velocity at time 2. All right, and we know that the instantaneous velocity or velocity is given by the derivative, right, of the position function. So the derivative of f here, using the chain rule, right, the derivative of 7 would be 0, then minus 1/2, bring that 2 down and drop this power by 1. And then take the derivative of the inside, which is 1, right? So you would wind up with minus quantity t minus 4. So that's the velocity function, which is the derivative. And then if we want to know how fast this particle is moving at time 2, right, then we would just plug in the 2, and we would get the velocity, or the derivative at time 2 is equal to 2. Okay, so this particle at time 2, right, is moving 2 units, right, to the right. Okay, so let's take a look at that. Back over here, we can see that this slider, which was giving us that, remember the slope of that line was the average velocity, and we got, when we shrunk it back, we get the instantaneous velocity. If you look at the slope of this line, the purple line, you can see it's over 1 unit, right? And then up 1, 2 units right there. So even though it's not really the tangent line, just really, really close to it, we can see that it's nearly 2 right there. Okay, the average velocity and the instantaneous velocity. So that matches up with what we had, right? And then if we go back here and turn back on the point and look at the motion, oops, wrong slider. We can see that the particle starts off here, and then at time 2, right here, so right when it gets to 5, this will be headed at roughly a speed of 2, right? Whatever units per whatever time unit you're looking at in this direction right here. So this, we can see right here that in 1 second later, right, it was at 5 and it went only 1.5 units to the right. So this particle here has to be accelerating. It kind of looks like it's probably slowing down, right? Because if it were speeding up during that time period, it would probably have gone more than 2 units to the right. But it didn't go even 2 units to the right. It only went 1.5. So it's probably slowing down. So let's watch and see. So sure enough, it was slowing down, right? But it definitely was heading towards the right, when it hits to this point right here. You can see it moving 2 units to the right there. Kind of slows down and turns back around, goes back that way. Okay. All right, so that is the situation for the velocity. The velocity is the derivative of the position function. The last thing in this video is acceleration, right? Acceleration, remember, is the rate of change of the velocity with respect to time. So what it turns out is that in a very similar situation, if you want the acceleration function, right, the acceleration function is the derivative of the velocity function. Okay, and so that would make, since the derivative velocity is the derivative of the position function, that would also make the acceleration function the second derivative of the position function. Okay, so the derivative, right, is the key to analyzing the motion of these objects, and really that's what the people who invented calculus were after. They wanted to know, hey, I need some theory, about motion. I want to be able to predict motion and answer questions about the motion of objects, right? And so if I know the positions of objects and I can observe them over time and see how they're moving, right? I want to be able to find and solve questions about how fast they're moving and what direction they're moving and whether they're speeding up and slowing down. And so the derivative is the key to all that, right? If you have the position function, you can take the derivative to get the velocity function and know the velocity at any moment in time. So it's, again, like the speedometer, right, for the position function. And then if I want to know the acceleration, right, of a particle, then I can take the derivative of the velocity and get that. So we can completely describe the motion of the particle.